Welcome back. In this lecture video, we're going to look at estimating the parameters of the multiple regression model. Now, to do this, let's set up some notation. So we will let n denote the number of observations in the data set. We'll let k denote the number of explanatory variables, the x variables. We'll let y sub I represent the response variable for the ith observation or the ith subject. And we'll let x sub ij denote the value of the jth explanatory variable for the ith observation. Now, associated with the regression model is an error term, epsilon. And for the ith observation, we would have an error term denoted by epsilon sub I. The assumptions that go along with the error terms are that they have an expected value or mean of 0, and that their variance is the same for all observations, and that common variance is sigma squared. Now, here's what the data for a multiple linear regression would look like. And you can think of this perhaps as a spreadsheet. That's a really good way to organize it and to think about it. And so rows correspond to observations, columns correspond to variables. And so we would have a column for the response variable y, and then you would have k columns for the k explanatory variables. You can see here that we have subscripted the response variable y with the subscript I, which again corresponds to the particular observation or subject. And then the regressors have been subscripted with double subscripting, x sub ij, again, I corresponding to the observation or the row in the data set, and j corresponding to the particular regressor or explanatory variable. So that is how we would organize the data set, and it's a good way to think about it in terms of conceptualizing what that data set looks like. And then so with that notation, we can represent the regression model for the ith subject or the ith observation in this way. So y sub I, the observed value of the response for the ith subject or the ith experimental unit, is equal to the deterministic component plus the error term. The deterministic component is beta 0 plus beta 1 times x sub I1 plus beta 2 times x sub I2, and so forth out to beta k times x sub ik. We can abbreviate that using summation notation. So we could write that deterministic component as beta 0 plus the sum, j going from 1 to k, again, j corresponding to the particular explanatory variable, of beta sub j times x sub ij. And then to that deterministic component, we have epsilon sub I, which is the error term for the ith experimental unit. Now, associated with this model, there are k plus 1 beta parameters, beta 0, beta 1, and so forth up to beta sub k. And so the goal is to estimate those parameters using the data. Now, in order to come up with an estimator for these, or estimators for these parameters, we have to have some criterion function. And the criterion function that is most often used in regression analysis would be the least squares criterion, the least squares criterion function. And the least squares criterion function is given by the sum of the squared deviations or differences between the observed value of the response and the predicted value of the response. And let me just say that in this notation, these betas ought to have hats on them, because then it would be much more clear here that what we're subtracting off would be the predicted values of the response variables. Now, this can also be represented in this way: the sum I going from 1 to n of the square of the error terms. And so again, in order to find the best fitting model in the sense of, or in the sense of least squares, we have to find betas, and in particular, and again, these ought to be beta hats. We need to find beta hats that minimize this expression. So this is the criterion function that we want to minimize. Now, once the data have been observed, in other words, once we have the y values, once we have all of the corresponding x values, then this least squares function is a function of k plus 1 parameter estimators. And again, what we want to do is find those estimators that minimize this function. Now, one way to do that is to utilize calculus. And so if you think back to your calculus class, one way to minimize this function with respect to these k plus 1 parameters would be to take the partial derivative of each of these beta hats individually, set that partial derivative to 0. That would result in a system of k plus 1 equations that you could then solve for the k plus 1 parameter estimators. And so that's the idea that we're going to look at here. And so on the next slide, we see here the first operation here is taking the first partial derivative of the least squares function with respect to beta 0 hat, and then setting that first partial derivative equal to 0. And so the first partial derivative of the least squares function with respect to beta 0 hat is given by this expression. And so we set that equal to 0. And then for the for j going from 1 to k, for each of the other betas, or other beta hats, beta sub j hats, we would take the first partial derivative of the least squares function with respect to each of those beta sub j hats. And so, for example, the first partial derivative of s with respect to beta sub j hat would be this expression here. And you set that equal, each of those equal to 0. And so again, that gives us a system of k plus 1 equations, which we can then solve for the k plus 1 unknown parameter estimates. And we can take the equations that result from taking these first partial derivatives and setting them equal to 0 and rewrite them just a little bit. And so, so that we have this form of those k plus 1 equations. And so notice that the terms that have the y values, we've moved over here to the right-hand side. And in this form, this system of k plus 1 equations is called the normal equations. So the least squares normal equations. And the solution to this system of equations gives us the vector of least squares parameter estimates. Now, another way to represent the system of multiple regression equations, let me go back here. So notice that we have this multiple regression equation for each observation, I going from 1 to n. And so we can think of writing this equation for each observation. So you would have y1 equal to, and then the right-hand side, and then y2 equal to the right-hand side, and then y3 equal to its right-hand side, and so forth, down to y sub n equal to, and then its expression for the right-hand side. And so we can think of representing that system in this way using vector and matrix notation. This is a single matrix equation. And so the left-hand side is the vector, the n by 1 vector of responses. So y1, y2, and so forth out to y sub n. On the right-hand side, we have this X matrix. This is a n by k plus 1 matrix, design matrix, right? It contains a column of ones that help us, or that allow us to have an intercept in the model. And then it has the values of the explanatory variables, the k explanatory variables for each observation. The beta vector is a k by 1 vector of parameters, beta 0, beta 1, and so forth up to beta sub k. And then the epsilon vector, that is an n by 1. It kind of looks like a k, but it's an n. So this is an n by 1 vector of error terms. And so using these vectors and this matrix, we can express the whole collection of multiple regression models, one for each observation, in this very concise way. Now that's useful because we can then specify the criterion function, the least squares criterion function, in terms of these vectors and matrices. And so, for example, if we were to express the least squares function as the sum of the squared error terms, then if we notice that if we subtract x times beta from both sides, we get an expression for the error vector. And so then we can rewrite that least squares criterion function in terms of these vectors and matrices. So the least squares criterion function, which is a function of the beta vector, right? Beta 0, beta 1, so forth out to beta sub k, right? That is equal to the transpose of y minus x times beta times the vector y minus x times beta. Now we can expand this and rewrite it a bit, and we get this equivalent expression for the least squares criterion function. So y prime y, or y transpose y, minus 2 times beta transpose times x transpose times y, plus beta transpose times x transpose x times beta. So this is a convenient way to write the least squares criterion function using the vectors and matrices that we have here in this representation. And so then the least squares estimators, the least squares estimator of beta must satisfy this equation here. And so again, what we're going to do is we're going to take this criterion function, the least squares criterion function, and because this is represented in vector and matrix notation, we're going to take the derivative of this function with respect to the vector beta, right? And I would describe it as taking the derivative with respect to beta hat, all right, and then setting that the resulting vector equal to the 0 vector. And so the least squares estimator of beta, the beta vector, has got to which is beta hat, has to satisfy this vector equation. Now we can rewrite just a little bit in this form: x prime x times beta hat equal to x prime times y. And so we can say then that the least squares estimator of beta, which is beta hat, has to satisfy this vector equation. Now you can we could do some mathematics on this, or you may just be able to look at this and realize that one solution, or a solution, and in fact the unique solution to this equation is when beta hat is equal to the inverse of x prime x times x prime y. Right. So if you just mentally substitute this expression here on the right-hand side of this equation in for beta hat, you immediately see that the two sides would be equal, because x prime x times the inverse of x prime x would be the identity matrix, and then you would have remaining on the left-hand side x prime y, and x prime y is certainly equal to x prime y. So that is how we can get a really nice expression for the entire beta vector, or the estimator of the entire beta vector. So beta hat using matrix representations and matrix calculations. Now, once we have the estimator beta hat, then the general formula for the fitted model for a generic y hat is given by x prime times beta hat. Now notice that this is a little x, not a big X, right? And so what this corresponds to is a representative set of explanatory variables for a particular observation. And so when you do this, when you calculate this inner product, what you get is beta 0 hat plus j going from 1 to k of beta sub j hat times x sub j. So it's exactly what you would expect to get, all right, by replacing the theoretical model and its deterministic component, those betas, replacing those betas with beta hats, all right? And so that's what you would get. Now, thinking about the entire vector of fitted values, so the vector of fitted values for all I of your subjects or experimental units, that would be given, well, number one, it would be represented by y hat. And again, this is bold, so this is a vector. So bolding means either vectors or matrices. So just keep that in mind. And so the vector of predicted values or fitted values of the response would be given by the product of the X matrix, which we know it's observed, right? That's the data, the values of the explanatory variables are contained in that matrix, so that's known. We multiply that against the vector of least squares parameter estimators for the betas. And so that would give us the fitted or predicted values of the response variable for the I observations. Now we can replace beta hat with what it's equal to, which again is from the previous slide here. Let me go back to that. X prime X inverse, X prime Y. So if we replace that in here, we get X times, and then X prime X inverse, X prime Y. Now it's useful to rewrite this a little bit, all right, in this way. We can write this as a vector H, a matrix H times the vector of observed response values. The matrix H, which is an n by n matrix, and it's given by X times the inverse of X prime X times X prime. And that matrix, that n by n matrix, is called the hat matrix. And it's called the hat matrix because that is the matrix that you multiply against the observed values of the responses to get the fitted values or the y hats. And so that is the reason that is called the hat matrix. And it's a useful abbreviation for this matrix expression as well. Okay, and so you will make we'll make quite a bit of use of this hat matrix. Now the residuals from the model, and in particular the vector of n residuals, can be conveniently and concisely written in matrix format in this way. So again, if we take the difference between the vector of observed responses and the vector of the predicted or fitted responses, then that gives us the vector, the n by 1 vector of the n residuals. And the residuals are, we can think of those as the estimated error terms. Again, the error terms, we never observe those, but we can estimate them. And that's what we're denoting by E. Now, in some textbooks and some sets of notes, you might see this represented as epsilon hat, but I think usually the lowercase e is used to represent a residual, or in this case, the bold e to represent the vector of residuals. Now, there's another way that we can represent the vector of residuals that's very helpful. And we get this by writing y hat in terms of how it's calculated, so X times beta hat. And so when we do that, you'll recall that we can, from the previous slide, we can rewrite this as Y minus the hat matrix times Y. And if we write it this way, then we can use properties of matrices and the distributed property to rewrite it as the product of the n by n matrix, identity matrix minus h times the n by 1 vector y. So that's another representation that we'll make use of as we go through the notes in the course. Now, here is an example. This is the delivery time data example. And let me just give a little background on this particular example. So this is the description of the example given in the textbook. This is on page 74 of your textbook. A soft drink bottler is analyzing the vending machine service routes in his distribution system. He's interested in predicting the amount of time required by the route driver to service the vending machines in an outlet. This service activity includes stocking the machine with beverage products and minor maintenance or housekeeping. The industrial engineer responsible for the study has suggested that the two most important variables affecting the delivery time, which is the response y, would be the number of cases of product stocked, so x sub 1, and the distance walked by the route driver, x sub 2. So it makes sense that the number of cases stocked and the farther the driver has to walk would certainly impact the delivery time. The engineer has collected 25 observations on delivery time, which are shown in table 3.2. All right. And so the goal here is to fit the multiple regression model given here, y, which is the delivery time in minutes, being equal to beta 0 plus beta 1 times x1 being the number of cases, plus beta 2 times x2, which is the distance in feet that the driver has to walk, and then plus a random error term. Now, obviously, the beta 0, beta 1, and beta 2 are unknown, so they've got to be estimated from the data. And so that's the goal in this example. We want to use the least squares criterion and then find the least squares estimators of these three parameters. Okay, so here is, before we do the analysis, it's always good to take a look at the data. And one way to visually assess whether a multiple regression model might be an effective way to model data such as this is to look at a scatter plot matrix. And so here we have our response variable, which is time, all right, corresponding to the first column and the first row. And then we have our two explanatory variables, so cases being the first and distance being the second. Those correspond to the second and third columns in this matrix and also the second and third rows. And so we see here, if we look at the scatter plot in the 1, 2 position, we see that we have a really nice increasing, and in fact, linear trend between delivery time and the number of cases. If we look at the scatter plot in the 1, 3 position, we see that we do have an increasing trend, but it's at least here, it's not nearly as good of a linear fit as the other one was. But there is an increasing trend, and we can imagine, superimposing a line over these data, and it may be a pretty good fit. But there is a little bit of I'm not sure how to characterize this, curvature or whatever, but it just is kind of funky looking right there. The other thing to consider is for example, this scatter plot in the 2, 3 position, and this is a scatter plot of the two explanatory variables, cases and distance. And we can see here that there's an increasing trend, and and it looks somewhat linear. And depending upon how strong that linear relationship is, that may cause us some problems in the fitting process, right? This could be an indication of some multicollinearity in the data. So that's something we want to keep an eye on. Okay, so let's continue on. Here is a 3-dimensional scatter plot of delivery time. And so we see here that we've got delivery time on the vertical axis. We have the number of cases, which is x1 on this axis. And then we have the distance traveled or distance walked on that axis. And so you can see here, to a certain extent, that there does appear to be an increasing trend as cases increases, and also as distance increases, all right, the delivery time appears to increase. But it can be kind of difficult with a plot like this to really see much of what's going on unless you have the ability to rotate the plot and look at it from different angles. And some software packages allow you to do that, some don't. Now, again, this kind of a plot is, in my view, of somewhat limited utility, because once you get beyond 2 explanatory variables, then how do you visualize that? I mean, if you've got 10 explanatory variables in your model, you can't fit a 3-dimensional scatter plot's not going to encapsulate all that, at least using the original variables. Okay, and then if we wanted to express the data in matrix format, then we see this is how we would do it. And so we see the vector of responses, right? So the y vector. So we've got 25 observations, and so this vector has 25 rows in it. And then we have the design matrix containing the values for the explanatory variables x1, the number of cases, and x2, the distance walked. And then we also have the first column containing 1. All right, and so these would be how we would, or what we would use to express the model in matrix notation. All right, so we need the matrix x prime x, or x transpose times x. And so this is how we would go about doing the calculation. And we would not want to do this by hand, obviously. We'd want to use a calculator or software to do it. And so when we go through and do that calculation, all right, we get the 3x3 matrix shown here. All right, and so this would be the number of observations, 25. This would be the sum of the of x1. 10,232 would be the sum of the x2 variable. This observation down here would be the sum of the squared x1 values. The 6,725,688 would be the sum of the x squared values, and the column, or the value in the 2, 3 position would be the sum of the x1 times x2 values. And then we also need the x prime y vector. All right, and so that's obtained by doing this calculation. And so this would be the result. All right, and so the first entry here would be the sum of the observations, the sum of the y values. The second value, 7,375.44, would be the sum of the x1 times the y values. And then the third value, 337,072, would be the sum of the x2 times y values. And then we can use these resulting matrices to come up with the least squares estimator for the beta vector. So to come up with beta hat, right? And so remember, beta hat is equal to the inverse of x prime x times x prime times y. All right, and so notice that in order to get this, we need to calculate the inverse. So you see that -1 up there. That's the symbol for the inverse of this 3x3 matrix. This matrix, again, is x prime x. And again, this is not something you would ever want to do by hand. We would use software to do this. And then we multiply that inverse against x prime y. And so when we do that, we get the vector, the 3x1 vector, containing these values. And again, beta 0 hat is equal to 2.3412. Beta 1 hat would be 1.6159. And then beta 2 hat would be 0.01438. And so once we have that, then we can write out the expression for the fitted model. So y hat equal to 2.34123 plus 1.615991 times x1 plus 0.01438 times x2. And so that shows the mathematics, the underlying matrix mathematics, to come up with the least squares estimator for beta 0, beta 1, and beta 2. Now, once we have the fitted model, we can plug in the values, the observed values for x1 and x2 for each observation to get the corresponding fitted value or predicted value for that observation. And so you can see here that for the first observation, the observed value for y was 16.68. Plugging in the values of x1 and x2 for that observation into this model right here, okay, we get a predicted or fitted value of y of 21.7081. So you can see that those two are not equal, are they? Perhaps, we probably wouldn't expect them to be. We would expect the predicted value to be a little off of that, hopefully not too far. And then you can see that for each observation, we can calculate the difference between y sub I and y sub I hat, and that gives us the estimated error term, or in other words, the residual for that fitted value. And we can do that for all 25 observations. And so here we have, again, the observed values of y, the fitted values of y. We take the difference between the two, and we get the corresponding residuals, which are the estimated error terms. Now, here is some output from Minitab showing the results of this analysis. And you can see here that right at the top, they give us the estimated regression equation, y sub I, or time, being equal to 2.34 plus 1.62 times cases, which is x1, plus 0.0144 times distance. Now, let me just say that they're abbreviating these quantities. The beta 0 hat is rounded to 2 decimal places. Beta 1 hat is rounded to 2 decimal places, and beta 2 hat is rounded to 4 decimal places. But in its internal calculations, it's maintaining the full precision for those values in the software. It's just abbreviating these for the sake of printing it out. Now, in the following table below, we have the estimated parameter values for beta 0, beta 1, and beta 2. All right, so Minitab has calculated the estimated value of beta 0 to be 2.341, all right, and rounded to 3 decimal places. That's exactly what we got. The estimated value for beta 1, so beta 1 hat would be 1.6159. All right, and again, if we rounded our value to 4 decimal places, this is what we would get. And then if we, the estimated value for beta 2 hat, the estimated value for beta 2, which is beta 2 hat, would be 0.014385. So that's what we want to focus on right now in this particular section. We'll look at the other values in this output later, but right now what we're focusing on are just the estimators of the beta parameters. Okay, so here is a nice way to interpret these squares. Okay, it's the geometrical interpretation. And so we think of the observation vector, so the y vector. It's an n by 1 vector containing the n responses. And by the way, let me just say that obviously if n is greater than 3, this is technically not accurate, but this is a useful way to think about it. And so just keep that in mind as we talk about this. But this y vector here corresponds to the observation vector. And then this plane down here corresponds to the model space that we're going to choose a model from. All right. And so we can then think of this vector here, x beta hat, as being a candidate for our fitted model. And the goal is to minimize the vertical distance between the observation vector and this point right here, and the point at the end of the model candidate. And it's clear that that that's in particular, we want to minimize the square distance. But we can see here that that distance is minimized when we pick a parameter point that gives us a model in this model space that is a projection of our observation vector into that model space. All right, and so we can see here that the length of this vector is longer than the length of that vector there. All right, and so this also helps us to see that the least squares estimator, the least squares parameter, which results in this particular fitted model, is unique. All right, and it also minimizes the square distance between the observation vector here and the end of that model vector. So that's this is a really nice way to visualize what's going on with least squares. Now, let's look at some of these statistical properties of the least squares estimators. We've talked about and shown how to calculate the estimator, but let's talk about the statistical properties. And so the expected value of the least squares estimator of the beta vector, so the expected value of beta hat can be shown to be the beta vector itself. And so what this means is that the least squares estimator for the beta vector is unbiased. All right, so that's an important property that we like our estimators to possess. And it can also be shown, and it's easy, or it's more convenient. It's easier to do this if we think in terms of the matrix form of the model. But the covariance matrix associated with beta hat, right? The covariance matrix associated with the least squares estimator of beta is equal to sigma squared, which again is the common variance of the error terms, times the inverse of x prime x. All right. Now, if we write x prime x inverse as the n by the matrix C, all right, and so it would be k by 1 by k by 1. Okay, so if we represent that matrix as using the bold C, then we can easily write out formulas for the variances and the covariances of the individual estimators. And so, for example, the variance of beta hat sub j, and this is a little typo in their notes here, all right, in their slides. This should not be bolded, right? This should be just a regular beta sub j hat. And so that would be the least squares estimator of beta sub j, the coefficient on the jth explanatory variable. The variance of that beta j hat is equal to sigma squared times c sub jj. Now, c sub jj is the diagonal element in the matrix cap C, which again is the inverse of x prime x. It's the jth diagonal entry. In addition, the least squares estimators of beta 0, beta 1, and so forth, beta 0 hat, beta 1 hat up to beta k hat, those are random variables. They're estimators, and they have a covariance between them. And so this shows that the covariance between beta hat sub I and beta j sub beta sub I hat, beta j hat, the covariance between those two estimators would be equal to sigma squared times the entry in this C matrix, C sub ij. So the entry in row I, column j of that C matrix. And so this is a way we now have expressions for the variance of the individual beta sub j hats, and then covariances between the ith beta hat and the jth beta hat. And this is going to be useful as we go on and look at additional issues associated with multiple regression. All right, so then we also, in order to, the additional parameter that we need to estimate, we've shown how to estimate the beta parameters, right? Beta 0, beta 1, so forth, up to beta sub k. But we still have one additional parameter to estimate, and that is the variance of the error terms, sigma squared. And so the first thing we need is to calculate the residual sum of squares. All right, this is also called the sum of squared error. All right, and using matrix notation, vector notation, all right, we can calculate this as y prime y minus beta hat prime or beta hat transpose times x transpose times y. All right, and so again, these are bolded, so we're talking about the y vector, the beta hat vector, the x matrix, and the y vector. All right, and so again, this is how we would calculate the sum of squares error, or also called the sum of squares residual. And the result is a 1-by-1 matrix, which we can just consider this as a scalar. All right, and so this is a number. And then to get the mean square error, or also called the mean square for the residual, we divide that by the appropriate degrees of freedom. All right, and so the residual mean square for the model with p parameters is going to be n minus p. Okay, and it can be shown then that the mean squared error, or the mean square residual, well, it gives us the estimate of sigma squared, So that's why we're denoting this by sigma hat squared. Okay, and so and that's how we get that. So in your first methods classes, you learned how to do simple linear regression, and also in the context of ANOVA, analysis of variance, we looked at problems that were simple enough that we could do these kind of calculations by hand. So we calculated the total sum of squared by hand. We were able to calculate the sum of squares error by hand, and so forth. And then we divided those quantities, those sums of squares, by the appropriate degrees of freedom by hand to get the mean squares. But as we step up in dimension, as we include more than one explanatory variable, it becomes much easier, at least, to represent those calculations using matrix notation. So that's why we're using that kind of notation here. All right, and so when estimating sigma squared and thinking about this estimator, we need to keep in mind that the estimator of sigma squared depends on the model, right? And so if we change the form of the model, obviously the estimate of sigma squared is going to change, because we've got different parameters involved, different parameter estimates, and so forth. And so the error variance, the variance estimate, is a function of the errors. All right, so going back to the example, okay, so now we're looking at example 3.2, all right, where we continue on. We've already fitted the model using the data in example 3.1. And now what we want to do is we want to estimate the remaining parameter, which is sigma squared. All right, so in example 1, we estimated beta 0, beta 1, beta 2. In this example, we want to estimate sigma squared, the variance of the error terms. And so we're going to use this expression here to get the sum of squares error, or the sum of squares residual, and then we'll divide that by n minus p to get our estimate of sigma hat squared. And so we have here the sum of squares error being 18,310.629. And then we calculate beta hat prime times x prime times y. Okay, we get 18,076.90304. We take the difference and we get the sum of squared error. By the way, I said sum of squares error up here. It's the total sum of squares. All right. And now we take the difference to get the sum of squares residual, also known as the sum of squares error, and we get 233.726. Okay, then we need to divide that by the appropriate degrees of freedom. In this particular model, we have two explanatory variables. All right, and we have a parameter associated with each of those explanatory variables. beta 1 and beta 2, but we also have a beta 0. We have the intercept in the model, and so that gives us p equal to 3 beta parameters. And so we divide the sum of squares error, 233.726 by 25 minus 3. All right, so n minus p, 25 minus 3, or 22, and we get 10.6239. And so that is our estimate for the variance of the error terms. We would use that then in constructing confidence intervals for predicted values, or confidence intervals for the slope coefficients and so forth. And this can be very, very useful. We also use it in the context of hypothesis testing, which is going to be the next section. And so that wraps up estimation for the multiple regression model. All right, we've looked at how to estimate the beta parameters and also how to estimate the variance of the error terms. Like I said, the next section is going to talk about hypothesis testing in multiple linear regression. And so we'll cover that in the next lecture video.